Hello everyone, welcome to the talk titled Better Secret Sharing via Robust Conditional Disclosure of Secrets. I'm Oded Nir from Tel Aviv University, and this is a joint work with Benny Applebaum, also from Tel Aviv, and with Amos Weimel and Nati Peter from the Ben Gurion University. So we are going to talk about first secret sharing schemes. We'll see some background and then present our new construction, which has the best parameters to date for secret sharing. We'll talk soon about what those parameters mean. And then we'll see conditional disclosure of secrets protocols, which were used in previous constructions for secret sharing. And in the end, the new robust conditional disclosure of secrets protocols, which we'll call from now on CDS, these type of protocols were used in our new construction for secret sharing. So let's begin with the secret sharing part. The most known form of secret sharing is a threshold one by Shamir and Blakley, where we have a randomized dealer holding a secret S and n parties, represented here by 6 dogs. And we want the dealer to give a share to each party. And we have a threshold parameter T, meaning that we want any coalition of T or more dogs to be able to take the shares they receive, perform some calculation, and recover the secret. And any coalition of size less than T, they should learn nothing from the shares they received about the secret. So for example, if T equals 3, then this triad should learn the secret, these also, but these two should learn nothing about the secret. But this is a very basic form of secret sharing. We're going to be interested in a generalization of it. And we're going to define access structures as a list of authorized coalitions. And we will want to share a secret now according to any type of access structure, any list of authorized coalition, not just the threshold one. So the very basic new example is an authorized coalition of size 3 and an unauthorized coalition of size 3. And apparently, this generalization makes the problem much harder. And we'll soon see how much harder. But first, we'll need to view some basic properties of access structures. So access structure is basically a list of subsets. So we're going to view them graphically with this rhombus representing the lattice of subsets, where in each line we have all of the sets of the same size. So the middle line here represents all of the n/2 subsets of the n parties, and at the bottom we have lines representing small subsets, and at the topmost line represents the all subsets, etc. So the next thing we're going to say is that access structures are monotone. And it means that if we have here an authorized coalition or set, then all of its supersets must also be authorized, since they can just recover the secret from the subset that is authorized. And from very similar reason, if we have an unauthorized set, then all of its subsets must also be unauthorized, since they have even less information than their superset. And due to that, this is how a typical access structure looks. It has authorized sets above unauthorized ones. And the last thing we'll need is to look at access structures in another way, which is with their characteristic functions, which are Boolean functions, also monotone like the access structures. And here, any coalition will be represented by n-bit strings with 1s for every player that's in the coalition. And the function representing the access structure will output 1 on a certain string if it represents an authorized coalition. If it represents an unauthorized coalition, the function will output 0. So now here, the middle layer represents strings of weight n/2, and the same for the other layers. So now we're ready to ask the question that we talked about, what are the parameters we measure a secret sharing scheme by? So the most important parameter for us will be the size of the shares dealt for each of the players. So we'll say complexity of an access structure is the minimal length of shares among all of the possible secret sharing scheme for that access structure. So for example, the complexity of a threshold scheme is quite low. It's log of the number of the players. And we have a big open problem, which is what is the complexity for general access structures? One algorithm that can deal shares according to any access structure. So let's review the history of the results in this field. So the problem of general secret sharing or secret sharing for general access structures was presented by Ito and al. In 1987 with a solution that gives shares of size 2 to the n. And it took over 30 years to improve this result in a big breakthrough by Yu and by Quintanatan, which improved the exponent here not by much quantitatively, but it's still a big breakthrough since they showed it's possible to go below 2 to the n. And since then, we've managed to improve it more. Last year, in this Eurocrypt paper, we got the exponent down to 0.897, and this work brings it down to 0.64 n, where the lower bound is pretty far ahead. We have a huge gap between the lower and the upper bound, as in many information theoretic protocols. And we don't know where the true answer for the complexity of this problem lies. Some conjecture that the true complexity is exponential in n, but we have no proof for that. And it's also interesting to mention a specific family of secret sharing schemes, which is linear, where the dealer is only allowed to perform linear actions on the secret and its randomness. And when we limit ourselves that way, the exponents come out a bit higher in all of the works, all of the algorithms. But here the lower bound is much higher, and we're probably closer to finding out the real answer about the complexity of linear secret sharing schemes. So after seeing that, now we are ready to discuss constructions of secret sharing schemes. And the thing that is in common to all of the schemes we listed before is that they all can be represented by a monotone formula. So let's say we start with some access structure that we want to share a secret to. We can decompose it to other access structure. Here with an OR gate, we can also do it with AND gates, and then do it over and over again until we reach very simple access structures that we can deal the secret to. So for example, decomposition of an OR gate means dealing the secret separately to each one of these new access structures, and then if a set gets the secret from one of them, then it will get the secret in total. For AND, it's quite similar. And so in this type of solutions, the share size must be bigger than the formula size for the worst case, since if we have 2 to the n leaves in this tree, one player can be in some set for all of these leaves. And we have in the worst case 2 to the n leaves, and that player will get a share with a size at least 2 to the n. And so in order to improve this, we need some sort of trick. So before getting to the real trick, first we'll see the first step LV did. Just to simplify the problem a little bit, they reduced the general secret sharing for a specific family of access structures where we care only about coalitions of middle size between n over 2 plus delta to n over 2 minus delta, and we just say don't care for anything else. And LV presented one reduction of this sort, and in the Eurocrypt paper we presented another, but now we're only interested in these mid-slice functions. So the real trick of LV was coming up with a new sort of gate for the monotone formulas, which we will call regular gate for regular access structures. We'll define it in a couple of more slides, but the general concept is that with these gates, we can build better formulas, smaller formulas, with the exponent they got to is 2 to the 0.994 n instead of 2 to the n, using these regular gates, and these regular gates come in our calculations almost free with sub-exponential cost, and that's due to CDS protocols, which we'll also talk about, and they got sub-exponential message sizes since Liu, Vaikuntanathan, and Wee's work in 2018. So that was LV's solution, and we offered something in the same spirit, but that got better result, which is using a different kind of gate for different kinds of access structures, which we will call somewhat regular access structures. And for them, the size of the formula will be polynomial in n. So we're actually moving the heavy lifting part of the algorithm from the size of the formula to the size of these new gates. So if we choose the parameters of the balancing parameters here correctly, then these new somewhat regular gates will cost us 2 to the 0.64 n, which is the cost, which is the dominant cost of the algorithm. And here the key ingredient will be this new protocol called robust CDS, which we will also describe. So we'll define now these access structures, the regular one, the somewhat regular one. The definitions are quite simple. So for the regular access structures, we have a fixed partition of all of the secret sharing players to k parts, here k equals 6. And we have another parameter d, which will equal 3 here. And we will only care about access structures where in each block of the partition we have exactly d players, or 3 players in our case. And any such coalition can have arbitrary behavior. They can be authorized or unauthorized. Here in this example, it's an unauthorized coalition, they're red. And this is a blue coalition, they're authorized. And for anything else, we just say don't care. And the somewhat regular access structure has a pretty similar definition, but now we have 2 threshold parameters, a and b. In this example, a equals 2 and b equals 4, and we will allow arbitrary behavior for all coalitions that have between 2 and 4 players in each block. And then otherwise we say don't care. And of course, this type of access structure is a much richer family that describes many more behaviors, and that's why the cost of the algorithm will move to building access structure for this kind of family and move out of the need to combine too many of these together. So that's the general concept, and now we'll move on to see what are those CDS protocols we're talking about and how robust CDS brings us new abilities. So conditional disclosure of secrets, first presented in the year 2000, also involves a secret and some players, but the concept is a bit different. Here we have Alice and Bob, which we will call servers, and Charlie, which is the referee. And Alice and Bob hold a secret S, and we want them to disclose it to the referee only when a specific condition occurs. And that is when the predicate that takes their inputs, Alice has an input X and Bob has an input Y, outputs 1. So if the predicate outputs 1, Charlie should learn the secret, and if it outputs 0, Charlie should learn nothing about the secret. And Alice and Bob do it by sending 1 message each to Charlie. They're not allowed to talk to one another, and Charlie even knows their input, so their only advantage over Charlie is their random string. So just stating it formally, correctness means that if the predicate outputs 1, Charlie gets the secret. If it outputs 0, Charlie can simulate the messages it's received without knowing the secret in advance. And the communication is the size of the messages. So actually in secret sharing, we use a K-server protocol for secret share for CDS, where we have K Alices and Bobs, sending each one message to the referee. And a few more important properties of CDS for us. First, that it has small communication, sub-exponential, as we mentioned before. And one limitation of CDS, that is the motivation for us to create robust CDS protocols, is that if by any chance Charlie gets more than one message from any of the servers, say Alice, let's say it gets a message corresponding to an input 000, and the message corresponding to an input 010, that were both generated in the same protocol with the same random string, somehow we got two messages, then in that case, we lose the privacy guarantee. The definition is undefined. It depends on the implementation of the protocol, but basically Charlie can learn the secret even if it shouldn't. Even if the predicate outputs 0 on all pairs of X and Y here. So it means CDS is not robust. So now we will see a definition for what is this robustness that we need. And the way we will create later robust CDS protocols is by taking a regular CDS protocol and immunize each one of the servers so they will be able to send more than one message with the same random string. And this process has an exponential overhead. So we'll define robust CDS with the same scheme here, and we'll only need to upgrade the privacy guarantee. And now say that if Alice has T inputs and it sends T messages to the referee, then if every pair of inputs, pair of messages of Alice and Bob is a 0 input of the predicate, that means that Charlie should not learn the secret from any pair of messages, then it should not learn the secret in total. Of course, if f of, say, x1 and y equals 1, then Charlie will just learn the secret from that, and there's no point of improving any privacy guarantee there. So we have, as we said, we'll need to do it simultaneously. We'll need to immunize both Alice for being robust and then Bob, and we'll need their simultaneous robustness. And we have two parameters here that are important. One is T, which is the number of simultaneous inputs Alice can send message for while still preserving privacy. And the other important parameter is the possible number of input vectors of size T, because we have many T tuples, and Alice can be private only for some of them. So we have to take that into account too. So another way to view this immunization process that we want Alice to go through is as if she had a one-time secure channel before in the CDS protocol. She could only send one message without compromising privacy. And we want to turn that channel into a T times secure channel for her to send T messages. And in fact, by now we have covered quite a lot of topics and new ideas. So if you had enough, feel free to go to the end and see the summary. But since it's a video talk and we have a little bit more time, I will cover this attempts to immunize Alice. And we do it with a reduction to the following channel immunization problem. So as we said, Alice has a one-time secure channel it can use, and we want to turn it into a T times secure one. And the way we start is using n one-time secure channels. So on each channel, Alice can send a message and it will come out on the other side to the referee. But if it sends two messages on the same channel, the security breaks and everything leaks. So Alice has T messages it wants to send. So a naive solution would have been to send one message on each one-time secure channel and then we are done. But the problem is that Alice has no memory and the messages come out online, so it doesn't know which channels she has used before. And the advantage that she does have in order to solve this problem is that every message is publicly tagged. So for every message we have a tag in a tag domain that corresponds to Alice's input. And the question now is how many channels are needed to deliver these vectors of T messages when we have a tag domain X, and that will correspond to the message size of the robust CDS protocol. So, of course, the number of channels must be bigger than T, because in the best case, you just send one message on each one-time secure channel. And the size of the tag domain is upper bound for us. And what we achieved is an upper bound of T times polylog of X to the T. And actually a more accurate answer uses the second parameter of the robust CDS protocols we talked about, which is not only T, which is the parameter of how many messages can be leaked simultaneously, but how many T tuples can Alice actually leak or be robust against. So if that number is L, then the number of channels we need is only T times polylog of L. And the way we do this and get to this number of one-time secure channels is in the following way. We use a method we call select and share, where Alice first hashes its tag of the message she wants to send. And that will tell her which one-time channels to use. But it doesn't send the message itself on each channel. No, it performs a secret sharing scheme and sends one share of the scheme on each channel that the hash function chose. So we still want completeness to hold. That means that if Alice sends a message only one, then the referee should be able to get it exactly as it is. That means that every message sends shares that are an authorized set of the secret sharing scheme. But we want robustness or privacy. So what does that mean? So we will first see what happens with two messages, which is the simplest thing to do. So each message is hashed by its tag to a set of one-time secure channels. And on each channel is sent a share of the secret sharing scheme. So when we send a second message, some channels are still secure since only one message was sent through them, but some channels are compromised. So the way we still get robustness or privacy is if these channels that had collisions on them that were compromised form unauthorized sets for the secret sharing schemes that we use. So that's the basic idea. We've implemented it in two different ways with two different sets of hash functions and their corresponding secret sharing schemes. And now we can move on to sum things up. So back to the outline, we've actually talked about secret sharing schemes. We've seen the background and on high level, from high level, the new constructions. We've defined conditional disclosure of secrets protocols and robust conditional disclosure of secrets protocols. And we've seen the main ideas behind taking CDS protocols and immunizing one of its servers so we can actually do it again and again and get to a robust CDS protocol. And if we come back to this picture of the complexity for secret sharing for general access structures, then we still have the open problems we started with. One is, can we get to sub-exponential general secret sharing? One thing that may help is sub-exponential robust conditional disclosure of secrets, since that's the dominant part of the cost of the schemes we now know. And of course, on the other side, an open question is, what is the lower bound? Can we get superlinear lower bounds, or even exponential lower bounds? So I hope we find out. Thank you very much for listening. Hope you enjoy the rest of the conference and that everyone around you is healthy and well. And until the next time.